Everyone here, everyone on the stream, definitely after you watch this, start working on it now. As you know, the first submission deadline is October 12th, so that means that you at least need to implement a baseline model, which is one of the biggest steps in the assignment. And then after that, you're going to need to give yourself a lot of time to experiment and tune, because it's not necessarily a quick process, and you want to have enough time. So once my clicker works, okay. Okay, that's working now. All right, so briefly, here's today's agenda. We're going to touch on the problem. We're going to touch on some data pre-processing techniques. We're going to talk about some model architectures that you guys can start out with, and some ones that you can experiment with down the line. And then we're also going to talk about the learning objective as well as some other losses that you can think about using. All right, so let's talk about the problem statement. So really what we're doing here is we're using transfer learning initially to design a system for speaker verification. And I say transfer learning because, as you guys have probably already seen, the first task that you're going to do is implement an M-way a network for M-way classification of speakers. But this is not necessarily the task at hand. So what we're really trying to do is we're trying to train a convolutional neural network to extract and learn features that are useful for speech verification, which itself is distinct from identification. So given these two embeddings that we learn, so given a pair of them from two different utterances, we need to come up with some kind of similarity metric, usually based on the distance between the two vectors given some distance function. All right, so here's a rough outline of the general approach. 2 speaker log spectrograms, generally variable length. Currently, right here, we're assuming that you've already trained this convolutional neural network, and it's going to produce a feature embedding, and we're going to use some kind of distance metric. This could even just be Euclidean distance between the two vectors. And this should give up, for well-trained feature embeddings, this should give us a good metric of similarity. All right, so one thing that we're talking about in this assignment that we haven't really talked about before is open set versus closed set problems. So generally, what we've been doing so far in the course is closed set problems, where you have a training set, and even though the data is different in the training set, we believe that it is generally distributed the same way as the test data, and we definitely assume that they're the same classes represented in the test set as there are in the training or evaluation set. Here, that's not necessarily so. Here, what we're doing is we're learning a data set of a fixed number of speakers, and then we're going to do verification on a data set that is likely disjoint from our training set. So the speakers that you could be testing on are not necessarily ones that you've trained on before. So the goal is to learn features that are general enough such that they're not fitting necessarily to the inconsistencies of a specific speaker. So here's a diagram of the problem. It also goes over the classification versus the metric learning problem. But we're going to talk about a bit about the problem of identification and the problem of verification. So the problem of identification, in this case, is a facial recognition task, but it's very similar, right? So the idea is that in identification, given a face, who is it? This is generally a closed set task, right? You have 1,000 known speakers, and we need to figure out who it is. In verification, all we need to say is, are 2 speakers the same? And other ways that identification is done is if you have some sort of gallery of faces that you know, and then you can use some sort of verification to run your test image through the gallery and see whether they're the same or not, and then try to identify the face that way. But that falls much more in the verification side of things. So today we're really just going to focus on verification.
So in the case of facial recognition problem, we had the training set.
Did it just go off?
Yeah.
A lot of things this morning.
So in the case of the facial recognition problem, we have our training set. Now there are two ways we can look at the problem. It can be a closed set or an open set face recognition problem. In the case of the closed set problem, what we're looking at is, so in this case, the identities all appear in our training set. And also, while we're doing verification, we're predicting the label. And so that's how we're doing. So we're predicting the label. So we are training our set such that each face belongs to a particular ID. And during the verification phase, what's happening is we are actually giving a face and we're asking our network to predict the ID. So in this case, and if we're given two faces, then we compare the IDs of both the faces. And then if they belong to the same ID, then we say they're the same person or not. So in this case, it's a classification problem where we're learning features of the data. Whereas in the case of an open set recognition problem, yes. Okay, yeah. What happened now?
What's going on? So
Okay, so in the case of the open set face recognition problem, here the identities do not appear in the training set. We're assuming, so it's not like the training set is completely exhaustive for all our training IDs. So what happens is when we are training a network, we are actually running a feature extractor where we extract features from each of these faces. And in the case of the verification phase, what we are doing is we are actually seeing if two faces are passed into our feature extractor, we're seeing how close these two features are. And we have a threshold. So if these features are very close, then we consider them to be the same. Whereas if they're not, it's not the same. So in this case, it's more like we're learning a margin. We're learning how far away can features be considered to be not considered the same identity. So that's where we get into the identification and verification phase. So there are two ways of approaching there are two ways of solving a problem where we're doing identification or verification. In identification, we are running a classification sort of a problem. Exactly in homework 1 part 2, what you guys did was an identification problem. In the case of verification, we are doing a 1-to-n matching, where you pick up a sample and then you find the closest sample among n other samples. But in this homework, what you will be doing is a 1-to-1 matching, where given two samples, you will verify if they belong to the same speaker or not. Now let's get into transfer learning. Okay. Okay, it's back. Yeah. So for transfer learning, the whole point is it's basically a machine learning method where a model developed for another task is being used as a starting point for the model for the second task. There are two main approaches which we will use. Two main approaches for transfer learning, which is the developed model and the pre-trained model. So in the developed model approach, we select a source task, then we develop the source model, and we reuse the model. So we start whatever model we had previously developed is used as a starting point for the second task, and then we further tune it. For example, in the pre-trained approach, what we do is we select a model which is already pre-trained. For example, some of the most popular pre-trained models are the ResNet 50s and the ResNet models, which are pre-trained on ImageNet data. And then we reuse that model, but we fine-tune further on the model. So what you can do is probably people just fine-tune the last few layers to make it more specific to their classification task than what's currently done the ImageNet task. So in the diagram, as you can see, we have an old classifier, then we extract the pre-trained, and then we have a new classifier. So that's the concept of transfer learning, where you're using something which was previously learned and using it for a new task. Now for this homework, how do we all tie everything together from what we had covered? So we are going to use transfer learning for this task of speaker verification. And we will follow the developed model approach. If you remember, that was we first train a model for our own task. for task 1, and then we fine tune it for task 2. So that for our model 1 would be training a convolution network to perform an n-way speaker identification. We have some speaker IDs in our data set, right? So using that, we'll perform a convolution network. We perform a classification task. After that, we extract the intermediate representations of these speaker recordings. And then, after we extract these intermediate representation, we verify if these two representations belong to the same speaker. But, so that's just not enough. We have to kind of fine tune the network to learn the features better, to learn more discriminative features. Because we want, it's not only a class identification task, it's a verification task, as we had mentioned previously. So how do we go about speaker verification? So in this case, given our recording in the log spectrum, we pass it the CNN, we have the embedding layer before the classification layer, and then we get the end class probabilities. So we use a cross-entropy objective, and it's applied per sample, as we had previously. That's kind of standard how we do it in the previous homeworks. How are we evaluating your network? So how are we evaluating this verification task? So we're using the equal error rate. So it's usually for binary classification problems, where we need a point where your false positive rate is equal to your true positive rate. So that's basically our ER point, according to the graph, if you see. So this is your precision by recall graph, and there's an area under the curve. So we need the point where both of them are equal is known as the ER point. So that's the values you see. So in your homework, if you get a value of 0.5, that's absolutely random, because you'll see it somewhere in the middle, right? So you need a better, so the higher your EERs, the lower your EERs, the better it is, all right? Now, what about your data? So the first approach towards solving any problem is how does your data look? So we have multiple recordings of different lengths. And in this case, I have plotted a histogram, and we can see the average length is around 9,700 features in each recording length. And as the chunks increase, we see the number of speakers also increase. So what I would suggest is start with chunk 1, get a model up and running, and after that, it's just adding more chunks to your data and letting it learn better, right? So as this data set is extremely huge, as you guys see, it was huger before. So we actually tried to reduce it slightly by using the voice activity detection. So what it does is it finds if there's a presence or absence of human speech. So the whole idea behind using the voice activity detection is that we want to remove parts which have no speech or are silent parts, because that kind of reduces our data set to a slightly lower size. But it's still, I think, around 1820 GB, if I'm not wrong, right? And so this is the whole process, where at the end we apply a classification rule, where based on a threshold, where we identify if it's a silence or if it's a speaker speaking. Right? And also one more point which we did was we reduced, so we have represented this data as 16-bit floats. So that way we are again, instead of a float 64 or 32, we have half the data size by reducing the representation size. Now, as we know, it's all variable lengths, so how do we handle it? Now, there are various ways where we can handle it. And using your previous data set statistics, you need to figure out a fixed length, which you think is most appropriate based on the previous numbers which I had shown earlier. So there are ways you can do it where you slice off a fixed length from the utterance, just from the beginning, or you can pick up a random point in the middle of the utterance and slice it off. And if your utterance length, if your slicing off is larger than your utterance length, then you repeat the utterance. So, can I do it here?
Watch the cable, please.
Yeah. Okay. So if this is your utterance, and at the moment and this is of like 20, and you have decided to slice off a length of 25. So what you do is, for the rest 25, you repeat this 5 over here, right? So you continue wrapping your data. So why this works in this task but not in the previous other tasks is because this is an identification task. We are not verifying what phonemes the speaker is speaking. We just want to learn features of the speaker itself. So that's why this works for this speaker identification problem itself. And you can use the np.pad function, which will help you wrap it easy, which will help you wrap your data easily. Now let's get into, yeah?
Can you explain the difference? Like, why wouldn't you just pad it with zeros?
So if you pad it with zeros, it becomes a silence. You can consider it as a silence thing, and you're kind of not giving more information. You're losing information. So if you had sliced off, like, okay, let's assume again, so this thing is 25, and your slice points are 20, right? But your random point which you've decided is 20. So you have 40 here. I mean, sorry, you pad it more, so you, right? So that's your whole new utterance, which is all zeros. But if you had padded from here, you have more information for the network to learn. So that's the reason we don't pad it with zeros, but it's more sensible to wrap it with the data itself, right? Another tip is, so we have the train load function in your utils.py. Don't load your data on your init function of your data loader, okay, if you're using the data loader. Load it outside and then pass it as a parameter, because I've noticed you get memory issues very quickly due to that. As you try, yeah?
I was just wondering, to clarify, like, at what point are we making this a fixed length? Is that before we pass it to our convolution network, or is that after we can transform the network going into the verification task?
Sorry, I didn't get you.
So when we're making our utterances a fixed length, is that before we ever give it to a convolutional neural network? After that?
So it's before you give it to the convolution network. Even while in your testing phase, when you're given two samples, you need to sample two utterances from both your speakers and then pass it into the convolution neural net for extracting the speaker embeddings. Yeah. Oh, yeah, and when you're training it too for the first time. I mean, it works both ways, because what you train it with, you need to even verify it with, right? Yeah?
So when you're training this, do you want to randomly slice it each time you go through the data sets? Is there a point in like slicing differently every time you go through one part?
No. I mean, slicing differently?
So
Wait.
let's say you go through the entire data set once. So is there a point in, because you are slicing to randomly, from the point, is there a point to randomly slice it again? Then
If you randomly slice, if you pick a single ordering at the beginning, you do that per epic. That's the same thing as having a fixed data set where you just arbitrarily pick the starting point.
Yeah, so you do
So
need
it is,
to slice it.
you do it again, so you get different starting points.
Okay.
So the network learns more features better, right?
Next time when you go through it again.
Keep random. So what I would say is in your get item or something like that, just keep a random function which generally slices data.
I see. So you feed the entire thing in there first, and when in the get item you do the slicing.
I mean, that's just a way to do it,
Many
but
ways to do it.
yeah, there are better, more efficient ways. So now let's get into the network architectures itself. So this is still, we are on the classification task. We are on the first model, right? So we have to train our CNN. So there's PyTorch gives us 1D convolutions and 2D convolutions. If you're using a 1D convolution, you set the number of channels as 64, which is your feature size. And while average pooling, you need to average across the time dimension. Make sure you do that, otherwise you get messed up results. And also you achieve low ERs, around 24 in the first few epochs. So a better way to do this would be 2D convolutions, where in this case, so as we had learned previously in our class, the 2D convolution is used basically on an RGB image, right? So that's why we consider 3 channels. But in this case, we are using speech utterances, which are basically a monochrome 2D image. So the number of channels we use is just 1 in this case. One more point about convolution 1D is it's as good as doing a time delay network, as convolving over time delay networks as we had learned it in class previously. So in a 2D convolution, we set the number of channels to 1, and while average pooling, so at the end you need to pass it through your MLPs, right, to extract your embedding. So you need to average pool twice, once across the dimensions and then across the features, right? You'll know when you implement it, you'll know. And also, you should achieve higher ERs in this case. So convolution 2Ds do work better than 1D. Well, the reason is that you're convolving not only over time, but you're also convolving over the features, Whereas in the previous case, you're not doing that. You're just convolving over time, right? And another memory optimization technique is to use tapering, where layers near the input can have higher filter sizes and larger strides, and you can reduce the filter sizes and strides as the network goes deeper. But make sure you handle your padding while you're doing this, otherwise you'll get errors, right? So this optimization technique is
So is it higher ER or lower ER?
I meant lower. I'll correct that. Yeah. So with these techniques where you can use so these are actually there in a lot of popular popular convolution architectures, which we will see next. So one of the first ones which came up was the AlexNet, where they were the first ones to use ReLU and dropouts instead of tanages. So that's why they were really popular, but it's 2012. It's when the network started, the convolution network started getting deeper, right? Followed by that, there was VGGNet, which was deeper than the AlexNet, right? And they used fully connected layers at the end. That was also something which VGGNet brought to the table. So the thing is, as these networks get deeper, what happens is your accuracy will, your error rate will keep decreasing, but then it'll stagnate, and after a while, it starts increasing. So you don't want that to happen. So just having a deeper or a larger network doesn't, I mean, if you keep training it, it does not always help. So that's where people came up with ResNet. So ResNets are these where they have like these networks where you have skip connections. So what you do is you take the input of a previous layer and you fast forward it to a deeper layer below, right? So that's and we use an identity function. Most cases it's an additive identity function where we add the input of the previous layer from the previous layer and the current input from the stacked neural layers, as explained here. So I'll put out the paper link with this slide, so you guys can refer to the paper for more further details on what is the exact. So there are multiple ResNet architectures like 50, 101. So the layers just get deeper, right? But they could get deeper networks. Because of these residual skip connections, and they achieved good results with this ResNet too. An extension of ResNets are dense nets, where instead of using an identity function, they're actually concatenating outputs from the previous layers, right? So, and because of and they also encourage feature reuse, and these networks are usually more narrower, okay? I'll also give out the paper to this. You can check out the architecture, and you can implement it for your homework. So these are some of the networks which I would say is a good start on how you want to do your homework and then tune it further. And you'll find a lot of literature online which will help you with implementing them too. Okay, I'll give it over to Ryan now for the next step.
Sure.
All right.
I'm gonna try to just start and restart the
Okay.
stream. So
This is a good time.
So
I'll just take a break.
They might have to refresh their.
Okay.
browser if they're watching it.
Okay. Can you post on Piazza? Yeah. In the meantime, does anyone here have any quick questions about anything else, or
How do you ever pull for the time?
I restarted it.
you restarted it? All right, I will get back to that question. Well, actually, I'll just say it on the stream. So we have a question about how do you average pool over the time dimension? Well, it's just mean, right? So the idea is that at least in PyTorch, you'll just have to take the mean over the correct axes of the tensor. So, yeah. All right. So now we're kind of going. We're going to step back a little bit. Let's recap what we went through. We went through the speaker verification problem. We talked a little bit about using classification for verification, using transfer learning. We talked about some practical data considerations in this task, convolutional nets for feature learning, as well as some useful architectures. All right, so next, we're going to revisit classification for verification. Why does it work? Why can we get away with this? We're going to talk about how we can actually explicitly optimize for more discriminative features. And then we're going to think about margins a little bit, and then we're going to go over some other losses that deal with optimizing for these discriminative features. And then lastly, we're going to touch on something called angular softmax, which is a really interesting variant of the softmax loss with a neat geometric interpretation. All right, so back to the slide that we had before, speaker classification, but for verification. So we're going to utilize the activations of the second to last layer. This is arbitrary. Sort of we have this intuitive idea that like this is the nearest point in the network, like we assume that a neural network builds features in a hierarchy towards higher level features. So we want to use the highest level features that are not just being used for the classification task. And then we're going to estimate the similarity between the speech samples by using the inverse distance between these embeddings. You can, pick what distance metric makes you happy or what works best. All right, so this is a slide that we went over in a previous lecture. And it's true that like deep neural networks can learn really meaningful features as they, to do the task at hand. So for example, you can see in this left image here how even though it's achieved the classification task well, the class labels that it assigns the next highest probability are usually very well related, semantically to the class that it's classifying, right? So like this leopard, leopard, jaguar, cheetah, snowcat, and so that's in classification that we can see that it has some good understanding of the features. But even more interesting, and this sort of motivates our use of the second to last layer as an embedding feature vector. And this shows that if we tear off the activity, the embedding, after a feed forward on the first image in the left column, and then we do that for the whole data set, and then we try to cluster. These are the nearest neighbors to that vector in Euclidean space. So that's pretty interesting. So now that we can say that we can use classification to learn useful features that are in line with the separability learned in classification. So remember that classification purely requires the separability of different of samples from different classes. It doesn't necessarily mean that you are maximizing interclass distance or minimizing intraclass distance. And when it comes to verification, the goal is not just to separate, but we really want to have discriminative features. And these are features that will really like, don't want to say discriminate, that's not going to work too well, but like they want to create a measurable, you make distance useful for telling multiple classes apart. So we need to define a measure of distance. Most often we're going to consider Euclidean distance. All right, center loss. So what if we define a criterion that promotes minimal intraclass distance, but on the same time maintaining interclass separability, but we're not necessarily going to explicitly promote that. So what we do is for each class, I believe this is MNIST. Yeah, this is MNIST here. For each class, go through and for all the examples, find a class center at every iteration, and then try to pull the embedding. This is the xi here, the feature vector, towards that class center. So obviously we're assuming Euclidean distance here, trying to minimize that between each sample in the same class. This is a yi, and the embedding vector. And often this will be a joint objective, where LS is just your normal softmax cross entropy loss. I'm calling it softmax loss That's sort of just a general term used to like consider the last layer, the classification layer, the softmax transformation, and then the cross entropy objective. But I'm just going to call it softmax loss. So you can use it as a joint objective. Often, though, you will use it to further fine-tune your network. So you will train on classification, and then at the end, apply center loss. OK. But this is not too, we can be a little bit more explicit about pursuing interclass separability. So now what we're going to try to do is maintain a margin between embeddings of different classes. So in contrastive loss, what we're going to do is for every pair of training instances, try to push these samples for intraclass embeddings together and maintain some margin M between interclass ones. So the idea of the margin here is that if two samples of different classes, if their distance is less than this margin, we want to penalize that. But if their distance is greater than M, then we don't penalize it in this objective. And so you can see in this objective here, it looks really fancy, but all it's saying is that if the class labels are the same, minimize the square distance. Otherwise, if they're not the same class, then we take the max here. So you can see if this distance is greater than M, then we're not going to penalize. If we're less than M, then we're going to try to push it away. So this is generally only really useful for fine-tuning because it's not an information-rich criterion. You can think about it as for each sample, joint sample, it's going to be a 0.5. If the set's balanced between positive and negative pairs, then it's going to be a 0.5 probability. So log of 1 over that probability is 1, log base 2, so that's 1 bit of information per sample pair. And it turns out that it's a bit tricky to balance sample pairs and also choose this margin. It's especially if the vectors are like not normalized. It's really hard to like think about what metric to pick or like what margin to pick. And then a practical consideration is like, how do you actually do this? How do you get two embeddings at once and then consider each of their contributions, or like how do you propagate gradients back so that way the samples are pushed away or pushed together as this objective says. So what we're going to do is we're going to have something that's generally called a Siamese network. So a Siamese network is really just two networks with shared parameters, where you think about it as just feeding through one network twice, producing two embeddings, and then applying this objective, and then backpropagating that error. Okay, so another interesting idea is called triplet loss. Now, not just two, but we're going to have three shared parameter networks. And with them, now we're going to have three samples. And the three samples we're going to call the anchor, the negative example, and the positive example. And this is very much motivated by nearest neighbor classification, which I'm sure you're familiar with. And the key idea here is that we want the speaker embedding for a given speaker to be closer to all the embeddings of that same speaker than it is to any embeddings from any other speaker. So it's really, we want a nearest neighbor scenario. So the goal here is we're going to share parameters among three networks. And then you can see in this diagram here, or basically as I described, that's what the objective is going to try to do. If you're interested in implementing this, the paper is linked, and you can follow it and see the exact criterion. Yeah?
What's the difference between this and center loss? Center loss feels like it's trying to like move the centers together in a kind of a similar idea. Like you're trying to move them away, yes, but center loss is still trying to do kind of a very similar idea.
It's a similar idea, but it ends up being mathematically different, because like here with center loss, every iteration you then pick a center and you try to cluster the points around that center, whereas in triplet loss, this is a per sample objective here. We're actually individually trying to push together the embeddings of the positive class with the anchor, and then push it away from the negative class. Triplet loss ends up working. It's really hard to give empirical results because it depends what domain that you're working in, but triplet loss can work really, really well if you can sample triplets in an intelligent manner. This is called sample mining. A lot of times you can get imbalance and the thing can really fall apart. So the only downside the big downside of triplet loss is the engineering you need to do to get the sample mining correct, and plus just overhead of sampling, balancing triplets, and then actually loading them in, having three sets of having the parameters, having three sets of shared weights. So those things are a bit tricky, but this is definitely something to try. Again, like contrastive loss, this is also for fine tuning. Don't use this as your initial objective because you will see very minimal benefit, minimal learning in the beginning. All right, so we're going to step back again and we're going to talk about something that you've seen a lot. And this is softmax loss, which I said before, we're just going to use that word to describe the last layer parameters, the softmax operator, and then the cross entropy loss. So for simplicity here, we're going to simply assume a binary classification case. So the idea is that we have two weight vectors that make up the weight matrix. W1, the W1 transpose X plus B1 is the first unit output. W2 transpose X plus B2 is the second unit output. And with the softmax formulation, this is simply just the probability of class 1 is given at the top, and the probability of class 2 is given here. And if we set these two terms equal, right, this is going to be the point where the percentage that we believe it's either class is 0.5. So this is what we're going to call the decision boundary. And when you solve for everything, this is what you get. It's pretty simple formulation. All right. So now we're going to talk about this idea of angular softmax loss. So one of the things that we don't get with softmax is really an interpretation of how it learns the placement of features in space. So what if we can combine the idea of Euclidean margin constraint, which we saw in contrastive loss, with softmax loss? So what we're going to do here is we're actually going to formulate an angular interpretation of softmax and project it onto a hypersphere, and we can use some really interesting geometric reasoning. So now with this, there's no need for sample mining, and the learned features in a special case are very interpretable, and you can obviously see that they're discriminative. All right, so let's just go through sort of understanding angular softmax. So this is what we had before, is the decision boundary when the so still the binary case when the class probabilities are the same. And from your favorite intro calculus or like geometry class, we can easily arrive at this. But theta I is going to be the angle between the weight and the feature vector, so x and wi. And if we assume that I is a unit vector and that the bias are zeroed, the decision boundary becomes the cosine of the angle between x and the W1 is equal to the cosine of theta 2, which is the angle between W and theta 2. So this is angle bisection. So what's cool about this is that x drops out. There's no real consideration about x here because so now all we're saying is in this special condition, the decision boundary is an angle bisector of the two weight vectors. So you actually see it here. So this is we're not actually at angular softmax yet. We're getting there. This is what the paper authors call the modified softmax loss. So this is the angular interpretation here. And you can see that the decision boundary, the learned decision boundary on this data set actually lies at the angle bisector of W1, W2. And the weight vectors themselves don't necessarily have to be unit vectors, and the biases don't necessarily have to be 0, but the geometric reasoning is not as clean. So for now, we're just going to assume that. And when you use that identity and plug it into the softmax formulation and apply cross entropy loss on it, this is what you end up getting here, where theta ji assumes that we're talking about the angle between the weight vector j and the feature vector I. So, yeah. All right. But now what we can do, which we couldn't do with the, now we have a sense of like the space in which we can impose a discriminatory constraint. Before in contrastive loss, we can just use some kind of distance metric. But now we can apply a discriminative constraint based on the angle between classes. So we're actually going to add a margin, m, cosine m of theta. And what this tells us now is that, so this top equation is for the general multi-class case. That's kind of hard to think about, but we can think about it in the binary class case here. So as we said before, theta 1, angle between weight vector 1 and feature vector. Theta 2, angle between weight vector 2 and the feature vector. So cosine m is the equivalent of saying that theta 2 divided by m, in order to correctly classify type 1, say that 1 is the correct label, and we need to have the weight vector such that theta 1 needs to be less than theta 2 over m in order to be correctly classified. And the reverse is true for the other class. So what this comes out to here is this nice geometric interpretation. So you can just see the Euclidean margin loss in a 2-dimensional manifold and a 3-dimensional manifold. This is the modified softmax loss. You can see that there's just a clear decision boundary at the angle bisector. But for the angular softmax loss, now you can see in order for it to be correctly classified, you have to be greater than the margin, m. Sorry, your angle has to be less than m over theta. Sorry, theta over m. And so now you can see how it's this loss will push your feature representation into these little angular regions, and it's necessarily more discriminative, because I can go back and you can see this here, how if you don't have a margin here, yes, you may get separability with this interpretation, but you're not going to necessarily promote interclass separation. So I would highly recommend going and trying to implement angular softmax loss. Another benefit is that you get to use it during the classification phase, which is much more information rich. So you can use this straight off the bat. This is not necessarily a fine-tuning technique. So it's sort of like one and done. You don't need to have the complexity of sample mining and then doing a classification training first, and then fine-tuning. Just use this. All right. What do you think? Are there any questions? We can definitely go through some questions. We definitely have some more time. We're done with our slides for now, but is there anyone on Piazza? No, okay.
So when you say implement this, are you saying go back to the previous slide and implement that math in your criterion object?
Yeah, but there are some things that you're going to have to consider. So for example, this term here, the cosine of m theta yi I, that you'll have to, it's the domain is what, from like 0 to like theta over m. So you're going to need to like transform that into some monotonically decreasing function that shares the domain of cosine of m theta between 0 and the point at which it recycles. So in the paper they list another function you can use. Yes, but effectively it's implementing this with a couple changes and a couple more considerations.
So is the paper pretty descriptive in terms of
Very descriptive. Yep.
how you go?
Yep. I believe it is one of these archive links here. And the paper is not actually called Angular Softmax. It's a paper about face verification.
So when we have just regular softmax, you're taking not necessarily just 2 classes, you're taking lots of classes.
Sure.
Softmax, right? How does this generalize to more than 2 classes?
Yeah, so I'm merely just doing the logic with 2 classes here. I don't have a good visualization of the multi-class case. There is one in the paper, but you can imagine lots of these little arcs of multiple classes here. But this equation up top is the equation for multiple classes.
Yeah, cool.
Yeah.
So it's not necessarily you're comparing pairwise compute for at the same time.
Yeah, it's the same. Yeah, I mean you sum over the different classes.
Great.
All right.
Any other questions?
Any other questions? People on live stream, try to if you can post on Piazza in the next 2 minutes, we can answer. Otherwise, we'll call it a day. And I'll be holding office hours tomorrow from 2 to 3. So if anyone has any questions or wants to go over part 2, I'll be there in LTI.